line integral of first kind. Line integral of first kind appears from problem of mass of curve. Let us have curve L, which is provided parametrically. X is x of t, y is y of t, and z is z of t, where t is from alpha to beta. And this curve is called smooth if first requirement is that x of t, y of t, and z of t are all continuously differentiable on interval from alpha to beta, and we have some vector tau that is x prime of t I plus y prime of t g plus z prime of t k is non-zero for every t in alpha beta. And second requirement that L does not cross itself. So this one will be the smooth curve, and this one won't be a smooth curve. If we have closed curve, then if we have closed curve, which means that x of alpha equals x of beta, y of alpha equals y of beta, and z of alpha equals z of beta, then we need that x prime of alpha equals x prime of beta, y prime of alpha equals y prime of beta, and z prime of alpha equals z prime of beta additionally. Let us consider in R3, in space of real numbers, some smooth curve L, and this curve has some mass spread onto it, and density of this mass is mu of x, y, z. We need to find mass of this curve. So we have curve L, and we split this curve into n pieces. Li, I is from 1 to n. And length of this element will be delta Li. And at any Li, inside any Li, we put a point Mi. Now we assume that on this interval density is constant and is equal mu of Mi. So we'll get that delta Mi, mass of one element, will be mu of Mi multiplied by delta Li by length. This will be mass. Here not mass but density. Then mass of all the curve will be approximately sum from I1 to n mu of Mi delta Li. And if we make these elements very small and we make number of elements tend to infinity, then we'll have exact mass of this curve, which will limit of maximum delta Li tends to 0 and n tends to infinity, sum I from 1 to n, mu of mi delta Li. And this sum is called line integral of first kind. Properties. First property is linearity, that if we have integral by L, alpha f of x, y, z plus beta g of x, y, z dl, this will be same as alpha integral by L f of x, y, z dl plus beta integral by L f of x, y, z dl. Second property, if we have some line and we split it into two smooth parts, then we have f of x, y, z dl will be sum of integrals by first part plus integral by second part. Third property is that if we have integral by L dl, this will be length of L. And fourth property, that this integral won't depend on way of integration. So if you have L, some curve connecting nm, then integral nm f of x, y, z dl will be same that integral by mn f of x, y, z dl. Differential of a curve. Let us consider some smooth curve L that is provided by equation y equals y of x. And its function is continuously differentiable on interval from a to b. Y of x equals c1 on ab. Let us split this curve L by n elements using points ai. So we split this curve and we get ai minus 1 here and say ai here. We will get delta li and some line connecting these 2 points. Here we will have delta xi, and here we will have delta yi. So this will be change of x, change of y. Now let us have a equals x0, b equals xn, delta xi will be xi minus 1, delta yi will be yi minus 1. And we can now consider line a1, a2 and so on, an, which will give us approximation of this curve. Using Pythagoras theorem, we will get delta li will be square root of delta xi square plus delta yi square. So, summing up everything, we get that L of AB will be approximately sum square root of delta xi square plus delta yi square, and making everything go to infinity, splitting this curve into infinite parts, so we get the maximum possible approximation, we'll get length of AB as limit delta Li goes to 0, maximum value of delta Li, and goes to infinity, sum I from 1 to n of this square root delta xi square plus delta yi square, and so we get the scene. From here we will transform it into every other form. Let us have y equals f of x. X is in a b interval, and we take average x that lies inside AB and consider interval ax, and inside this interval length L will be L of x, not constant but some variable. Using formula for differential, we get dl will be L prime of x dx. Now we get L prime of x. Using formula for differential, we get limit delta x to 0, delta L over delta x. Actually, this is definition of a variable, which will limit delta x tend to 0. Delta L is square root of delta xi square delta x plus delta y square over delta x, which will be limit delta x to 0 square root of 1 plus delta y over delta x square, which is the same as square root of 1 plus y prime by x square. So dl will be square root of 1 plus y prime by x square dx. Same when we have x equals x of t, y equals y of t, parametric curve. Now we get dl, which is square root of 1 plus y prime x square dx, but now x is not a variable, it's a function. So we will be getting square root of 1 plus y prime by t over x prime by t square x prime by t dt. And finally we get x prime by t square plus y prime by t square dt, which will be formula of differential of L of our curve for parametric form. If we have three-dimensional parametric curve, x equals x of t, y equals y of t, z equals z of t, then we'll just get x prime t square plus y prime t square plus z prime t square dt. If we have polar coordinates rho equals rho of 5, we will get dl as square root of rho prime by phi square plus rho square d phi. Applications of line integral of first kind. We can find length of L. It's just integral by L dl. We can find mass of L, integral of L of density dl, static moments, m by yz or by xz or by xy accordingly, will be integral by L. Here we put x or y or z, this variable that is not included here, and multiplied by mu of x, y, z, dl. And we also can find coordinates of center of mass. We just divide myz by m by mass to find coordinate x of center of mass, and same for yc, mxz our mass, and zc will be m of xy our m. This will be coordinates of center of mass.